All right, everyone, let's start the class. All right, so first, I just graded half of your exam two. So if any of you haven't got your exam two graded, no worries. Right, just give me more time. Right, too many questions. Right, and um, so after exam two, right, until the final exam, we will cover just the two chapters, right, chapter 20 and chapter 21. So actually these two chapters, we just cover um, some other kinds of analysis in business field, right? So um, we will not talk about these topics in more details, just to give you a basic introduction about, for example, what is the time series, right? If you have a time series, how you can deal with it, right? And what are the methods to make the predictions, right? And also for the chapter 21, we will talk about the data mining. Right, so instead of just look at the book, right? The book just give you some concepts of the data mining, but I think the more important thing for this course is to give you more practice, right? So in our real life, you can deal with some detailed cases, right? So I will introduce two commonly used methods in the data mining, right? So the first one we'll talk about the decision trees, which is very important for the industry field, right? And another one is called the market basket, right? Which is important for the stores, right? So for example, the Walmart, the big stores, something like that. All right, so for this chapter 20, right, we'll talk about the time series. Right, so what is a time series? We say any problem with regarding the time, we'll consider it is a time series problem. Right, so we say if your data set is recorded over time, right, and then if you consider the time is a very important factor to your response variable, then this is a time series problem. Right, so in our real life, we have several very hot topics that's related with our time series, right? The first one is about the machine learning, right? So actually they learn the different activities just based on that we record the humans activities by over time, right? And then they will have the machine learning, right? And then another hot topic is if I want to simulate your voice, right? Some student may think I just just kind of edit your voice and copy paste together, right? So actually it is not that case. We just make a record or record your voice for example, every milliseconds, right? And then your voice will be modeled by some regression models, right? So that's based on your original voice, I can just create another, for example, another new sentence, right? So actually exactly use your own voice, right? So that will be the two hot fields right now related with the time series, right? But of course, in our course, we will not talk about these topics. We will just make a basic introduction about the time series, and then we will talk about some basic methods for predictions. All right. Okay, so we have already talked about what is a time series, right? So we say if your data is recorded over time, so it doesn't matter it is yearly or monthly or daily. All right. So as long as your time, the the time is equally spaced, right? Then it is called the time series, right? So you can record your values um, monthly, daily, yearly, uh, um, quarterly, right? And every minute, every second, every 5 minutes, every 10 days, right? So all of these ones, as long as your time is equally spaced, right? Then um, this data set is called a time series, right? So once we have for example, in this example, we have the Whole Foods quarterly sales, right? So that means for each year, they have 4 sales recorded, right? And then we say the sales is still considered as the response variable, right? But now our explanatory variable will be the time, which is our year, right? Then it is called the time series. That means the sales will be affected by the time, by the year, right? So actually from this plot, you will see that you have an increasing trend, right? So actually when the when the time goes, the sales of the Whole Foods increases. Right, so in this case, we call it is a time series. All right, and then we say just like in the beginning of this semester, we talked about the normal distribution, right? So whenever we have a new plot or a new concept, right? So we always want to describe this. Right, so just like in the normal distribution, we want to describe its center and variation by the mean and standard deviation, right? We want to describe the shape of the normal distribution, right? It is bell-shaped, symmetric, single-peaked, right? So actually, for the time series, the same thing, right? Once we have the time series, we want to describe these 4 components. Right, the first one we want to describe is trend component. Right, so let's look at the trend component. Right, so again, let's look at this example. Right, so we say for the Whole Food sales, right? So the overall, we look at the overall pattern of this plot, right? So from this plot, the overall pattern is getting increasing, right? So then we call this time series has a increasing trend component. Right. The other way, if you have a time series shows the overall pattern is decreasing, right? Then we say this time series has a decreasing trend component. All right. It doesn't matter it is going strictly or curved increasing, as long as it shows an increasing trend, right? Then it says, we say this time series has a increasing trend component. All right, okay. And the other case is if this time series doesn't show an increasing trend or decreasing trend, instead keep actually kind of the same, right? So it doesn't matter how much you jump up, above or below this line, right? It always come back, right? So it could go up and then go down, go up, go down, but actually the overall pattern, it keep the same, right? So for this special case, we call it is stationary in mean, right? So in this case, this time series doesn't have the trend component, right? So even though this is a time series, it is very possible that it doesn't have the trend component, right? So in this case, that will be stationary. That means no trend component. But for this time series, in the first example, it shows the increasing direction, right? Then it said that we say this time series has an increasing component. All right, okay, and then next we look at the seasonal component. Right, so what is a seasonal component? Again, let's use this example. Right, so we say this whole food sales is recorded for the 4 quarters in a year. Right, so actually, if you look at these points in more details, right, so for every year, it looks like the first quarter is actually higher than the other one. The first one is higher than the other three, higher than the other three. So actually, they roughly follow the same pattern. Right, so although this this pattern is not exactly the same, but actually they follow roughly stable pattern over time. Right, so then in this case, we say this time series has a seasonal component. Right, so we say if this pattern repeats within years, all right, then we call this time series has a seasonal component. All right, so here is another example. We say this is the Home Depot sales, right? So you can also see that they repeat every 4 points, right? So then this is another example for the seasonal component, right? So here we have 2 more concepts. Right, the first one is the deseasonalized. Right, so what is a deseasonalized time series? We say when we want to make the analysis about a time series, right, sometimes we do not want to include the seasonal components in our analysis. Right, we only want to focus on their trend component. Right, then we want to remove this seasonal component, right? And then this process will be called the deseasonalized, right? We call this time series as a deseasonalized time series. That's the seasonal component has been removed. Right, so of course, in our course, we will not look at more details for how to remove this component. And so as long as you know what is the deseasonalized, that will be okay. All right, and then another concept is the period. So what is a period? We say in this example, right, we look for example, for 2002, I have a peak, right? And then for 2000, next peak is actually this point, which is in 2003, right? So that means the time between these 2 peaks will be called one period, right? So in this case, that means what? That means your period is equals to 1 year. Right? And then we say for the seasonal component, we look for the repeated pattern within each year, right? So that means your period may be less than 1 year, but at least it should be less equals to 1 year, right? Then we call this repeating pattern as the seasonal component. Right, so again, if you can find any repeated pattern within years, that means the period is less equals to 1 year. Then we say this time series has a seasonal component. All right, okay, and then next one, we call it is the cyclical component. So what is a cyclical component? Again, we look for the repeated patterns, we look for the cycles, but now we look for the patterns that repeat for more than 1 year, longer than 1 year. For example, this repeated pattern happens every 8 years, every 5 years, every 2 years, right? Then this cycle or this repeated pattern will be called a cyclical component. All right, okay. And then the last component will be called a regular component. right? So what is a irregular component? We say in some time series, right, we do see some random fluctuations. For example, in this global temperature divisions, right? So actually, um, we see that the the points keep jumping about the mean, right? So you cannot find or you cannot see that this jumping is because of the seasonal component or the cyclical component, right? So actually you cannot find any use for these jumpings, right? So we call them our random fluctuations. Right? Or we short for, we just call them as the noise, right? Because it just, you cannot just find any U to model these kind of activities, right? So then to describe these kind of random fluctuations, or sometimes there is some outliers or spikes, right, cannot be modeled by the previous components, then we call them are the irregular components, right? So generally we say if in the time series you see a lot of random fluctuations or you see some outliers or unusual spikes, right, then that means this time series has a irregular component. All right. Okay, and then we always can find this irregular component from either just directly from our time series, or we can just get a residual plot, right? So to see any patterns, right? So then let's look at this example, right? So here, this is the example for the data set from the U.S. Bureau of the Labor gives the output per hour labor and output unit capital, right? So this is the time series, right? So actually this is recorded from 1985 until 2005. All right, again, um, can any of you turn on your cameras so that I can see someone? It's just talking to myself is so boring. All right, thank you guys. All right, so once we have the time series, right, and then we want to describe it, right? So first, describe the trend. Is there any trend component in this time series? Think about it. Sean?
I don't think so.
No, right? So perfect. Good job. All right. So actually from this time series, we look for the overall pattern. That means we do not care it is decreasing here, increasing here, decreasing here, increasing here, right? So we look for the overall pattern. So if you look at the overall pattern of this time series, you don't have any increasing trend or decreasing trend. It keep the same. It go up and then come back, go down, come back, right? So there is no trend component. Next, is there any seasonal component? So what is the seasonal component? We look for the repeated pattern within each year, right? So is there any seasonal component in this time series? Brianna? Brianna. Okay. Emily, what do you think?
I think there is.
There is? All right. So can you describe how it is repeated?
Yeah, like when it dips right, like 1992, and then it dips again at like 2002. To me, that's like a 10-year interval, so I feel like it's gonna go up after, and then it's gonna go down again.
So remember the seasonal component will be the repeated pattern within 1 year. But actually this repeated pattern actually repeats more than 1 year, right?
Yeah.
So that means what? That means in this case, we have the cyclical component, but not the seasonal component. You see the difference?
Yeah.
Okay, good. All right, so actually let's look at the seasonal component in more details. We say the seasonal component, that means we look at each year and then we see within each year, is there any repeated pattern for every year, right? But now if you look at this point, this data set is actually, this point is for 1991, 1992, 1993, 1994, and then 1995. So actually this time series is collected annually, yearly, right? So actually between 1990 to 1991, you even don't know what happens within that year. So of course you cannot find any repeated pattern within years, right? So then we say there is no seasonal pattern within years, right? Then there is no seasonal component. But as Emily said, right? So actually it's going down, going up, going down, going up, right? So actually you have a repeated pattern. You can consider like this one repeated again in this period, right? So actually this pattern repeat about, we know it is more than 5 years, right? So actually kind of repeats every 8 years, something like that, right? So of course it is, the period is always larger than 1 year. So it is a cyclical component. All right. And then the last one, a regular component. That means not regular, right? Cannot be considered as the trend, seasonal component, or cyclical component. Is there any random fluctuations? Is there any outliers? Is there any spikes? Very significant spikes. So actually in this time series, there is no these conditions, right? So actually everyone, just every point is collected for each year. So actually they kind of follow the same pattern for every 8 years, right? So in this case, there is no random fluctuations, right? So there is no kind of outlier or spikes. So there is no irregular component, right? So actually, in summary, we say if you are given a time series, we actually look for what? We look for the overall trend, right? We look for, is there any seasonal patterns within each year? We also look for, is there any long-term cycles that the period is larger than 1 year, but we do not expect to see this irregular component because there's nothing or no way to model this kind of component because they are all random fluctuations, right? So actually we can model these three components, but we cannot model this irregular component. They are errors, they are residuals. All right, okay, so actually we are done with describing a time series. And now remember, once you have the time series or once you have any data set, all right, our goal is always to make the predictions, right? So since we have the time series, the time is very, very important. Then if you want to make the prediction for the future, we have another word, right? We call it is the forecasting, right? So actually these two words are kind of the same thing. But if your prediction is about the future, then we are making the forecasting. All right, okay. And then we say, if you have a time series, then we generally use two kind of methods, right, to make the predictions or forecasting. The first kind we call the smoothing method, right? The other one is called the regression-based modeling methods, right? So now let's look at what is the smoothing method. For example, right? So if I have this time series, right, then you can see there are many random fluctuations, right? The points kind of keep jumping in the small fields, something like that, right? But actually, we do not want these random fluctuations. We want to smooth away of these random fluctuations. We want to smooth away of these noises, right? Then actually I can generate a smooth curve based on these points, right? So once these points are smoothed, then based on this data set until this point, I kind of know what will happen in the next point. Right, so that would be our smoothed method. I first generate a smoothed curve based on this time series, and then based on the smoothed curve, I can make the prediction for the next point. Right, and then for this smoothing methods, right, the good thing is you don't need to assume a trend or seasonal component, right, for this time series. In another word, we say there is no limitation for the time series, right? So as long as it is a time series, it doesn't matter it has the trend component or doesn't have the trend component. It doesn't matter it has the seasonal component or doesn't have the seasonal component, right? We can always use this method to make the prediction, right? Okay, and the bad thing is, since there is no limitation for the time series, that means actually it is better for the random fluctuation, is more friendly to the random fluctuations, right? So then in this case, we can only use this method to forecast the near future, only for the next time point, right? Or several time points in one time period. Right, so for example, if you have this time series, if you use the smoothing method, you can only make the forecasting of the next point. For example, will be the October 2012, right? That's it, right? You cannot make the prediction for, let's say, 2013, 2015, something like that, right? You can only make the prediction for the next data point. All right, so that will be the smoothing method. We say once we have the time series, we generate a smoothed curve. And then based on this smoothed curve, we can make the prediction for the next time point. Good thing is there is no limitation for the time series. You can have any kinds of time series. The bad thing is you can only forecast the near future, which is just limited to one time period. Right? Because what? Because the activities or the points are not stable. Right? You don't know what will happen in the longer future. All right. Okay. Next, we have another method we call the modeling method. Right. And then for this modeling method, we have already talked about in the last 4 chapters, right? We have the simple regression or multiple regression. All right, so if you have the regression-based modeling method, then we kind of can generate an equation, something like this. Right, so now based on the time, we kind of can generate an equation for the response variable or the cells. That means this relationship is very stable. That means whenever I plug in the x value, I can always make the prediction for the response variable. Right, so this relationship should be very stable. Then we say there will be a limitation for this method. If you have a time series, this time series should have a trend component or a seasonal component or even both of these two components. Then we will prefer to use the modeling method, because once you have the trend or the repeated pattern, then we can always model it. This relationship is very stable. Right? Then we can use the modeling method, right? And again, since this relationship is very stable, then we can use this relationship to forecast a further future, more than one time period. Right? So for example, I have a data set, a time series from 1990 to 2005. Right. Then I can use this relationship to make the forecast, for example, 2006. I can even make the prediction for 2007, no problem, 2008. But my question is, can you use this relationship to make the prediction for 2021? Actually, no. Right. Even though this relationship is stable, it is actually stable for the a little bit further future. But if it is 2021, that would be too much further, right? Then it would be the extrapolation. All the conditions has already changed, right? So you are not sure what will happen in 2021, right? So the good thing is once you have a time series with a trend or seasonal component, then you can set up or get a stable relationship between the time and the response variable to make the prediction for the further future. But again, you still need to be very careful that you cannot make the prediction for a very far away future. All right. Okay, so generally, for the time series, we just focus on these two classes of the methods. So of course, there are many methods in the smoothing methods, a lot of modeling methods covered in the regression-based modeling methods, right? So here in today's class, we'll just focus on the first method, right, which is the smoothing methods. Right. So again, we say for the smoothing method, we kind of generate a smoothed curve based on the observed time series, and then we want to smooth away the rapid or random fluctuations so that we can get what? We can get what is the underlying activities, right? Okay, and then we say for the smoothing method, the most commonly used method is the first one, simple moving average method. Right, so this belongs to smoothing method. Right, the first thing we can use the simple moving average method to smooth the curve. Right, so from the name we can see, okay, first it is a simple method. Right, so next we use the moving average. So what is the moving average? So before we look at all of these concepts and the formulas, right, let's just look at this example first. Right, so in the last example, right, so this is the DJIA dataset, right, so which is the Dow Jones Industrial Average dataset, right, for 2012. All right, and then we have the original data set, right, before this plot, we have all of these values, right? So actually it is from from the January 2012 until the September 2012, right? So actually it is recorded, I think it's every week, 2 months. No, not every, it will be every day, right? So then we have all of these values. Okay, and then what is the moving average? We say we short for MA, right? And then most of the time it will come with a number, right? So MA5 or next one MA15. So what does that mean? We say this 5 is the length. So that means the L equals to 5 for this case, right? So what is this L? L is the length that you want to get the average. So for example, this is the original data set, right? And then if we want to get the average or estimated value for this data point, then what I need to do is from this data point, I go up until I get 5 of them. All right, and then I make an average of these 5 values so that I add up all of these values, divide by 5, so that I have this value. I call this value as the estimated value at this time point. Right, we call it is the estimated. Or sometimes we also can call it is the averaged, right? Averaged Y value at this time point. All right. Okay. So this is the first estimated value. Next, what about this time point? Since the L equals to 5, right? So that means from this point, I need to go up until I get 5 of them. So that means you get the average from the second until the sixth. Right? And then you average these 5 values, and then you have another estimated value of Y. So actually you get these values just by moving these 5 values. So that's why it is called the moving average. We take the average for each 5 time points, and then we move this average or move these 5 time points to the next 5 points to get the average again. All right, so that will be our idea of the simple moving average. All right, so this is about the moving average with L equals to 5. Another example, if I set L equals to 15, that means what? That means our first estimated value will happen at the 15th, right? So that means you are averaging all of these previous 15 values, and then you average these 15 values together, and then you get the first estimated value, right? And then how to get the next estimated value? You move from the second until the 16th. Right, next one would be the third until the 17th, so that you get the next estimated value of Y. Right, so then this is the idea about how you get the estimated value or the simple moving average. Right, now one question, what about these previous four, these first four values? Is there any available moving averages, or is there any available estimated value of y? The answer is no, right? Not available because what? Because L equals to 5, right? So that means if you want to get the estimated value for this point, that means you need to average the previous 5 data points, but actually you only have 4. So for this point, not available. The same idea, not available for these ones. Right, so again, if L equals to 15, that means the first 14 of them not available. Your first estimated value will be from the 15th. All right, so now once you got this idea, right, now let's come back to these concepts. Right, so we say first, the moving average replaces each value in the time series by an average of the adjacent values. Right, we take the average of the adjacent values. Right, next, the numbers of values used to construct each average is called the length of the moving average. Right, you want to average the 5 of them, or 10 of them, or 7 of them, or 11 of them. That would be the length L. It will always be given to you, right, before you do the simple moving average. Right, and then once you have the length of L, we denote the moving average as MA of the L given, right? So that's, for example, in our example, we have the moving average of 5, we have the moving average of 15, right? So that means what? That means your L equals to 5 in this case. In this case, your L is 15. All right. Okay, so that will be the simple moving average, right? And then this is the general formula, right? I will not ask you to understand this general formula, right? So that means totally you need to get sum of all these values together and divide by how many of them, right? So this is the idea. All right, and then we say once we do these two cases, right? So we say one is MA5, that means the L equals to 5. Another one is MA of 15, right? And then based on these two columns, the calculated two columns, I can plot these values in the same time series plot. Right, so in this case, this red one is the original time series. And then I can plot another two time series. The first one, I have a yellow one. I have a blue one, right? Think about which one is for the MA5, which one is for MA15. We say, what's the difference between these two curves? The blue curve is more smoothed. Let's say smoother, right? So the moving average with L equals to 5 should be the yellow curve or the blue curve. It should be less smoothed or more smoothed. Think about the process. We say when we do the moving average of 5, that means we are averaging every 5 data points. For the moving average 15, that means we are averaging every 15 of them. So which one should be more smoothed? The 15 one or the 5 one? Any volunteer?
B15 is smoother.
15 should be smoother, right? Perfect. Good job, right? So actually we are averaging more values together, then the points should be more smoothed, right? Or in another word, we say if I randomly choose 1 point in these 15, but actually you sum up all of these 15 data points and then divide by 15. So actually, if you have a change to this data point, this change will not affect the estimated value a lot because it is averaged by 15, right? So then we say the longer moving average, the curve will be smoother because you are averaging more data points together. All right. But the other way, we say, since you are averaging more points, then if you have any rapid changes, then the reacts to these rapid changes will be slower because this change will only it will be divided by the longer moving average will be divided by the larger L, right? So then the change will be, the reacts to these changes will be very slow, will be slower than the smaller L's. All right, okay. So we say, if I give you this kind of time series with these two curves, right, and I tell you which I have, one is for L equals to 5, the other one is for L equals to 15. You should be able to identify, right, which one is for MA5, which one is for MA15. Right, so we say the longer, or we say the larger L, the smoother curve we have. All right, okay. And here we say, here is a example, right? So we say we have this following table shows the number of emergency calls to the fire department over the past 10 weeks. Right now, use the simple moving average method to calculate the available moving averages with L equals to 5. That means you should be able to calculate the averages, or we call the estimated y of t, right? So that means we have one more row for each week. All right, okay, so I will give you 3 minutes to practice by yourself. We say L equals to 5, right? So that means you are averaging the 5 data points, right? So then we say what? We say, is there any available estimate for the week 1? No, right? Because you need to average the previous 5 values, right? And then the same idea for the week 2, week 3, not enough, right? So until the 5th week, then you can average these 5 values, right, to get the estimated value for the week 5, and then you need to switch or move your average to the next 5 for the week 6, right, something like that, right? So try it by yourselves. All right, Matthew, what is your first estimated value for y?
22.4.
22.4 for the 5th week, right? Perfect. Good job. All right. So actually you are averaging these 5 data points. All right. What about the week 6? Mary.
Or would
So
it
that means
continue
for
being
the,
2.4?
so actually we are calculating the estimated y of t for the 6th week, right? So that means we start with the 6th week and then look for the previous 5 of them,
Oh, so it
right?
just carries on, like it
Yeah,
doesn't necessarily have to be week 1 through 5. It can like it just you just take 5 weeks.
yes.
So
So
2
that
through
is
6. Oh,
right. So actually, that is why we call it is the moving average. So actually, we set the L equals to 5, then every 5 data points. So what you get?
sorry, I'm just recalculating it now. I got 21.8.
Perfect. Good job. All right. So one more. Ethan?
I calculated it wrong, so I have to recalculate it.
No problem. Take your time.
Am I supposed to go like multiple weeks and back to calculate the forecast, or is it just like the week
So
beforehand?
we want the estimate value for the week 7, right? So then we
Mhm.
start with the week 7 and then go previous until we have 5 data points.
Okay. Can I try the next one and then just have someone do this one so I can see it
Yeah,
because I'm
sure.
calculating it.
I can. I got 21 for that
You
one.
got 21? Perfect.
Mhm.
Good job. Thank you. All right, and then if we keep doing, right, so for week 8, that means we start with 22 and then until 25, so that we have 5 values here, right? So then if you average, you have another 21 for week 9, very lucky, right? Another 21, right? And then the last week, right? So anyone want to try? What about the estimated value for the 10th week? That means what? That means we need to average from 19 and then
21.2.
go above, right? So then we say the average of these 5 would be 21.2. Thank you. All right, so now we got these estimated value of each week, right? So for the first 4 weeks, they are not available because the L equals to 5, right? So we start with the 5th week. All right, and then we say, remember our goal is to make the forecast, right? So we want to make the predictions. So how we can make the predictions? We say the prediction for the next time point will equals to your estimated value of y in the previous time point. Right, so you can also write it like this, right? So if you want to, let's say, if I want to get the estimated y value for the 11th week, that means we will use the previous estimated value. So that means we are looking for the estimated y at 10th week. Then what is the prediction for the 11th week? Will be just a 21.2. Got the idea? Right, it will be simple, right? So it just depends on the previous estimated value. Simply like the other example. Right, My question is, what is the predicted or forecast for the 6th week? Anyone? Gavin? Any idea? No idea. All right. So remember, if you want to make the forecast for 6th week, that means you need to use the estimated value for the previous week. You see the relationship here? Right. So if you want to get, I think that will be, this is the formula in the book, but I think it will be easier for you to understand for this formula, right? So if you want to make the prediction for the time t, then you need to use the estimated y value for t minus 1, which is the previous time point, right? So that means if you want to get the predicted value of y at the 6th week, then you need to use the estimated y value at the 5th week, right? So what is that? We have already calculated, right? 22.4. Right. More generally, we say we just add one more row for the predictions. Right, so that means since you do not have the estimated value for the week 0, something like that will be not available, right? So since this is not available, so here is also not available, not available, not available, right? So if the predicted value for the 5th week, that means we need to look for the estimated value for the 4th week, right? So since this is not available, that means here is also not available. But now next, the predicted y for the 6th week, we use the estimated value for the 5th week, the previous week. Right? The prediction for the 7th week would be the estimated value for the 6th week, right? So just a kind of a switched relationship. Then for the 11th will be 21.2. Got idea? All right, perfect. Okay, so now this is the simple moving average, right? So actually it is simple, right? So once you set the L, you just average all these points and then you get the estimated value and then you just switch the position, or we use the previous estimated value to make the prediction about the future. All right, and then we say the simple moving average is also called the naive forecast. Right, it is very good word, right? So this is actually this method is a naive forecast methods. Right? Why? Think about the whole process when we do the it doesn't matter the forecast or the prediction. Actually, we just average these 5 points. So that means each point has the same weight in our prediction, right? Every point takes 20% in our prediction. They have the same weight. But actually, in our real life, most of the time, the recent values should play more important role in prediction, right? So for example, if I have a time series that I record my height over time, right? When I grow from 0 until 18 years old, right? Then which one is more important for my prediction for my height in the next year, which is when I'm 19 years old. Of course, the height of the 18 years old should play more important role in than other previous heights, right? So then we say the simple moving average is a method for the naive forecast because we assume every point plays the same role in the prediction. But in our real life, we want to assign different weight for recent data points and all the previous points, right? So we want to assign a weight for the recent values, and also I want to assign a weight for all we call the historical values, right? Because they should play different roles, they should have different weight in prediction. Right, then we will talk about a advanced method, right? It is still moving average method, but now it is not simple moving average method anymore. It is called the weighted moving average method. Right, so for this method, actually there are many ways to assign different weights for different points. But here we will just introduce one of them. We call it is the exponential smoothing method. Right, so what is the exponential smoothing method? Here we just introduce a formula. Right, so we say we assign the alpha. Here the alpha we call it is the weight that is assigned for the recent values. Right, then that means what? That means 1 minus alpha will be assigned to the weight for all historical values. All right, in this formula, I kind of give you this idea. We say, if I want to get the estimated value at the point t, then I want to use the alpha, which is the weight for the recent value, which is y of t, right? So I want to use the weight times the observed value for this t, for this point. So we say alpha times the recent value plus the weight for all historical values, right? So this 1 minus alpha will be the weight for the historical values, and then what are the historical values? It will be represented with the previous estimated value of y. Right, so we say these two are about the recent values. These two together is actually about our historical values. Right, alpha is the weight for recent value. 1 minus alpha, that means not recent value. That will be weight for the historical values. All right. Okay, so before we go through all the details about how we can calculate this YT, right, think about these three cases. All right, so we say, what if alpha equals to 0.5? If alpha equals to 0.5, that means the weight for the recent value will be equals to the weight for the historical values. Right, so that means all the values take the same weight. Then we just have our simple moving average method, right? Everyone takes the same weight, right? They have the same weight for recent value and all the previous values. All right, next, what if your alpha is close to 1, larger than 0.5? What will happen? if alpha is close to 1, that means the weight for the recent value is close to 1. That means the recent value is more important in your prediction, right? The historical values will not be very important to your prediction. Then that means what? That means your prediction will be more closer to your recent values. Is that right? Right, so let's think about this case again, right? So we say if alpha is close to 1, that means the weight for the recent value is very high, right? So that means what? That means the recent value plays more important role in the prediction. Then when you make the prediction, when you calculate your prediction should be very close to the recent values because it depends more on the recent values, right? Okay, the other way, if the alpha is close to 0, what does that mean? Less than 0.5, close to 0. That means the weight of the recent value will be very small, right? So that means the recent value is not as important as the historical values, right? So that means the recent values are not very important. Instead, the historical values are more important, right? But since the historical values are about all the previous values, right? Then we say your estimated value or your prediction will be more about the historical values, not close to your recent values, right? Okay, so then again, if I have this plot, right, we know that one of them is 0.75, one of them is 0.1, right? So I have one purple, one yellow, right? I have two curves, smoothed curves, right? Which one is which, right? Let's just say, okay, which one is alpha equals to 0.75? The purple one or the yellow one? Think about it. We say since the alpha is 0.75, that means which one is more important? The recent value is more important or the historical values are more important? Alpha equals to 0.75. That means recent value is more important, right? So now think about it. If the recent value is more important for your prediction, then your prediction should be very close to your recent value, right? So that will be which curve? Will be the purple one. Should be very close to your recent or observed values, right? Instead, the other way, alpha equals to 0.1, very close to 0, right? So that means the recent value is not very important. All the previous values are more important. Then, of course, your smoothed curve should be away from your recent value. It will be all depend on your previous or historical values, right? So then we say it will be this yellow curve, right? And again, the yellow curve will show more smoothed, right? Because what? Because it depends on all the previous historical values, right? It's just like you have a larger L, right? So that means you will have a smoothed curve, more smoothed curve for alpha equals to 0.1. Got the idea? Let's repeat again. right? Remember, just remember the alpha is set to be the weight for the recent value. Recent value is actually just our observed value, what you observed. Okay, so if you are getting the estimated value for week 10, right? Then what is your recent value? That will be what you observed in the 10th week. That will be your recent value, right? And then all the previous ones from week 1 until week 9 will be the historical values. Right, so then we say if alpha is larger than 0.5, close to 1, that means recent value or what you observed is very important at that time point, right? Then all of other or previous time points are not that important. That means your curve or smoothed curve will be very close to your observed time series plot. All right. Okay, so next class we'll continue with the exponential moving average with a detailed example, right? But now what you need to know is what is our idea, right? So we actually assign different weight for recent value and historical values, right? So that they are not the same. Alpha is not 0.5. Right, they play different roles in your prediction. All right, so again, once you can calculate the estimated value of t, right, you can always get the prediction for the next time point. All right, okay, I think that will be it for today. Any questions? Another thing is for the next class, I think we can finish the class early. So I will give you time in class to complete your essay assignment 7. Right, so that you'll still have enough time to talk about your project 2. Right, so remember your project 2 is about 10 days away from today. Right, so don't think that 10 days is long time, right? So actually for project 2, you need to try a lot of things, right? So first, you need to make sure your possible model should pass the F test, right? And also you need to make sure each predictor should be significant, right? Then you will have one possible model, and then you need to think about changing the variables so that you have 3 or 4 possible models, right? And then we say, I do not require you to add any categorical variables into your model, but at least you should have the adjusted R squared to be larger than 0.70. Right, that would be a possible good model. Right, and another thing is in the previous semesters, some students can even try to get a adjusted R square is 0.95 or 0.96. That means the model is quite good. Right, so you can keep trying, keep adding the variables, deleting the variables, and then keep different variables. And for example, I create a dummy variable for this categorical variable to see, okay, whether this variable works or not. Right, so actually project 2, you don't have any accurate answers. Right, what you need to do is keep trying. Right, I think that will be all I want to talk about. And again, for the memo, the structure will be again the same, right? So how you deal with your data set, right? So did you delete the possible outliers, right? And then did you check your assumptions, right? How you get these models, possible models, and then how you compare these models. What are the evidence that, okay, once I choose this model as my best model, why, right? So you need to show why this model is a best model you can find. And then once you have the model, you want to make the prediction, right? And then you want to make the interpretation for each coefficient, right? And then once you have that, you want to make a conclusion based on your equation, right? So you have so many things to do. You have a lot of things to write, right? So just like if a company give you this data set, right, what you can do, what information you can give. All right. Okay, so that will be it for today. If you have any questions, just unmute yourself. Otherwise, let's see you on Friday. Thank you, guys. Any questions?
Thank you.
Thank you. Any questions?
Thank you.
Thank you.
I have a
Thank you.
question.